Almost everyone's first picture of electricity is the same. You imagine something flowing through a wire, the way water flows through a pipe. Turn on the switch, and the electricity rushes in, filling the bulb, making it glow. It's a comforting image, simple, visual, and deeply wrong. The trouble isn't that the analogy is useless, it's that it sticks around far too long. It quietly shapes how people think, even after they've learned formulas, symbols, and rules, and once that image is lodged in your mind, it becomes very hard to see what electricity actually is. This is exactly the kind of misunderstanding Richard Feynman loved to dismantle, not because people were ignorant, but because they were too comfortable with explanations that felt right without being right. Here's the first crack in the water pipe story. Nothing important in a circuit is moving fast inside the wire. The electrons themselves drift incredibly slowly. In many everyday circuits, they move at the pace of a crawling insect, millimeters per second. If electricity really worked like water flowing down a pipe, your lights would take minutes to turn on after you flip the switch. But they don't. The effect is nearly instantaneous. And that alone should tell you something fundamental is wrong with the picture. What actually happens when you close a switch is not that energy pours into the wire and travels down its length. What happens is that an electric field is established throughout the entire circuit, and that field rearranges charges everywhere at once, at speeds limited not by electron motion, but by how fast information propagates close to the speed of light. In other words, electricity is not a thing flowing through wires. It's a relationship established across space. The wire's role is subtle. It doesn't carry energy the way a pipe carries water. It constrains charges. It provides a path along which fields can organize themselves. The real action happens in the invisible structure around the wire, not inside it. The wire is more like a guide rail than a delivery tube. This is deeply counterintuitive, and that's precisely why the misconception survives. Our brains evolved to reason about solid objects, pushing and pulling each other locally. Electricity doesn't play by those rules. It's distributed, non-local, system-wide. Psychologically, this matters more than people realize. When we imagine electricity as a substance, we also imagine control as something linear, push here, effect happens there. But real electrical systems don't work piece by piece. They respond as wholes. Change one part of the circuit, and the entire field configuration adjusts. That's not just a lesson about physics. It's a lesson about how reality often works beneath the surface. Feynman was famous for insisting that you don't really understand something unless you can see where your intuition fails. And electricity is one of the cleanest examples of this failure. The equations are not hard because nature is cruel. They're hard because our everyday metaphors are inadequate. Once you let go of the water analogy, something powerful happens. Circuits stop being mysterious collections of parts and start becoming unified systems. Voltage stops being a push. Current stops being a stream. Electricity becomes what it actually is, the organized behavior of charges responding to fields in space. And that shift trains the mind. It teaches you to distrust explanations that feel right but hide contradictions. It encourages you to look for structure instead of stories, relationships instead of substances. So the real misconception about electricity isn't just technical, it's mental. We mistake models for mechanisms. We confuse convenience with truth. And if there's one thought worth carrying forward, it's this: the moment you stop asking what is flowing and start asking what is interacting, you don't just understand electricity better. You start thinking more clearly about the world itself. Once you let go of the idea that electricity is something flowing inside a wire, the next step feels almost shocking. If the energy isn't rushing through the metal, then where is it? And this is where Richard Feynman deliberately forced people to confront an uncomfortable answer. The energy isn't in the wire at all. It's in the space around it. That statement alone sounds wrong to most people the first time they hear it. We're taught to focus on the copper, the electrons, the hardware. The empty space around the wire feels irrelevant, like a background detail. But in electromagnetism, that empty space is where almost everything important happens. When a circuit is operating, energy flows through the electromagnetic field surrounding the wire. The wire's job is not to transport energy like a conveyor belt. Its job is to shape the field. It sets the boundary conditions that tell the field how to arrange itself. The wire is more like a riverbank than the river itself. Feynman loved this idea because it stripped away false intuition and replaced it with something simpler and more honest. You don't have to imagine little packets of energy racing through metal. You just have to accept that fields are real physical entities, capable of carrying energy and momentum through space. If that sounds abstract, consider a simple example. Take a battery connected to a resistor. The energy that heats the resistor doesn't travel through the wire into it like fuel through a hose. It flows through the surrounding space and enters the resistor from the outside, guided by the fields created by the circuit. The wire merely tells the energy where to go. This flips the usual picture completely inside out. And psychologically, this is where people resist the most. We're comfortable with objects. We trust things we can touch. Fields feel invisible, mathematical, unreal. But physics doesn't care about our comfort. The equations and the experiments are unambiguous. The energy density lives in the field. The direction of energy flow is described by the pointing vector, which points through space, not through copper. What makes this insight so powerful is that it explains something that otherwise seems mysterious, how circuits respond so quickly. When you flip a switch, the energy doesn't wait for electrons to travel the length of the wire. The field rearranges itself across the entire circuit almost immediately. The energy flow adjusts everywhere at once, limited only by the speed at which changes in the field can propagate. This also explains why focusing too much on the wire leads people astray. If you obsess over the electrons alone, you miss the system. You miss the interaction between charges, fields, and geometry. Electricity is not a local phenomenon, it's global. Feynman often warned that misunderstanding fields leads to shallow understanding. You can memorize rules, calculate currents, and still miss the point entirely. The point is that nature doesn't move energy the way we move objects. It distributes influence through space itself. There's a philosophical lesson buried in this that goes far beyond circuits. We tend to give credit to the most visible parts of a system and ignore the structures that quietly do the real work. Wires get the attention. Fields do the job. The same mistake shows up in organizations, ideas, even personal growth. We focus on the surface and miss the underlying relationships. Once you see electricity this way, the world looks subtly different. Empty space stops being empty. Connections matter more than components. The question shifts from where is the energy to how is the system arranged? And that shift is the real value of Feynman's insight. He wasn't just correcting a technical error. He was training people to see reality as it is, not as intuition wishes it to be. So if there's one thought to leave hanging in the air, it's this. The most important forces in your life, just like in electricity, may not be inside the objects you're staring at, but in the invisible structures connecting them. Once you understand that the energy isn't racing through the wire, another puzzle immediately demands attention. If the electrons themselves are moving so slowly, why does everything happen so fast? You flip a switch and the light turns on almost instantly. No waiting, no delay, that apparent contrariety. Qishan is one of the clearest signals that our intuition about electricity is misleading us. This is where Richard Feynman loved to pause and smile, because the answer is simple, but only after you abandon the wrong picture. In a typical household circuit, the electrons drift at speeds measured in millimeters per second. That's not a typo, millimeters. If you could watch a single electron, you'd be bored long before it made meaningful progress down the wire. And yet, the moment you close the circuit, the bulb responds as if something fast just happened. What happened wasn't fast electrons. What happened was a fast reorganization. When you flip a switch, you change the electric field throughout the circuit. That change propagates at a significant fraction of the speed of light. Every electron in the wire feels that shift almost at once and begins to respond locally. No single electron needs to travel from the switch to the bulb. They all start moving together, like a crowd that collectively leans forward when a signal is given. A useful analogy, carefully used, is pushing a long rod. push one end and the other end moves almost immediately, even though no atom travels from one end to the other. The disturbance travels, not the material. Electricity works the same way. The signal moves fast. The carriers respond slowly. This distinction matters more than it first appears. If you confuse electron motion with energy transfer, you miss the essence of how electrical systems behave. Electricity is not about transport over distance. It's about coordination across space. This also explains why circuits behave as unified systems rather than chains of cause and effect. When the field changes, it changes everywhere. Each charge responds to local conditions, but those conditions are part of a global pattern. The system adjusts as a whole. Psychologically, this is a tough pill to swallow. We prefer linear stories. Step 1 causes step 2, which causes step 3. But electricity doesn't respect that narrative. It operates more like a conversation than a delivery service. Every part is listening at once. Feynman emphasized this because it exposes a broader habit of mind. We tend to assign importance to motion we can imagine and ignore influences we can't see. Slow electrons feel insignificant. Fast field changes feel abstract. But in reality, it's the invisible, fast-changing structure that does the work. This insight also dissolves a common frustration people have with physics. They ask, if electrons move so slowly, how can anything electrical work? The answer is that the electrons aren't the point. They're participants, not messengers. The message is the field. Once you see this, a lot of confusion falls away. Power lines, antennas, even digital communication make more sense. Signals travel quickly, not because matter moves fast, but because information reorganizes space efficiently. And here's the deeper lesson hiding underneath the physics. Speed is not always about motion. Sometimes it's about responsiveness. Sometimes the most important changes happen not because something travels far, but because many things adjust together. That idea applies well beyond electricity. In learning, in organizations, in personal change, progress often looks slow if you track individual components. But shifts in structure, how things are connected, can transform everything almost instantly. So when you hear that electrons drift slowly, don't take it as a limitation. Take it as a clue. Nature doesn't rely on frantic motion to produce fast results. It relies on deep coordination, and that's the reflection worth holding on to. Real power doesn't come from racing ahead. It comes from understanding the structure that allows everything to move together at once. As the picture sharpens, another deeply rooted confusion has to be cleared away, one that quietly undermines almost every intuitive explanation people give about electricity. We casually talk about voltage as if it were a force, a push, a kind of pressure that shoves electrons down a wire. It sounds reasonable. It even sounds mechanical. And once again, it's just wrong enough to cause lasting misunderstanding. Richard Feynman was particularly careful here because he knew that confusing voltage with force leads people to treat electricity as a crude mechanism instead of a subtle condition. Voltage doesn't push anything by itself. It doesn't act. It doesn't move. It simply exists as a DI efference. Voltage is a condition that allows electric fields to form. That may sound like wordplay, but it's a fundamental shift in perspective. Force implies action. Voltage implies possibility. A cliff doesn't push a rock, but once the rock is there, gravity does the rest. Voltage is like that cliff. It sets up a situation in which charges respond. What actually causes electrons to move is the electric field, and the electric field exists because there is a voltage difference. Confuse those roles and the whole story becomes muddled. You start asking why voltage forces electrons through resistors, or why it gets used up, when neither of those ideas is even meaningful. Voltage doesn't get consumed. Current flows, energy transfers. Voltage simply defines the landscape. This distinction matters because electricity is not about brute force. It's about structure. A high voltage doesn't mean electrons are being bullied harder. It means the conditions are arranged so that a stronger field can exist, and that field influences charges everywhere in the circuit. Once you see this, a lot of common confusion evaporates. People wonder why birds can sit safely on high voltage power lines. They assume voltage itself is dangerous. But danger comes from differences, not absolutes. Without a difference in potential, there's no field doing work on charges. Psychologically, this is another place where intuition betrays us. We're wired to think in terms of agents pushing things around. Electricity doesn't work that way. It works through constraints and conditions, through relationships rather than commands. Feynman often emphasized that good physics replaces bad metaphors with better ones, or removes metaphors altogether. Voltage as pressure is useful only up to a point. Past that point, it blocks real understanding. Pressure pushes fluid. Voltage doesn't push electrons. It creates a context in which fields exist and fields influence charges. This also explains why voltage alone tells you almost nothing about what a circuit will actually do. High voltage with no path does nothing. Low voltage with the right conditions can do enormous work. The behavior emerges from the whole arrangement, not from any single quantity acting alone. There's a philosophical lesson embedded here that's easy to miss. We tend to overvalue force and undervalue structure. We look for the thing that makes something happen and ignore the conditions that make action possible. Electricity quietly teaches us that outcomes depend less on pushes and more on configurations. In life, we often ask what force will drive change. More effort, more pressure, more intensity. But change, like current, flows when conditions are right, when paths exist, when differences are meaningful, when resistance is understood rather than ignored. Understanding voltage correctly trains a more mature way of thinking. It shifts attention from aggression to arrangement, from exertion to insight. It reminds us that power doesn't come from pushing harder. It comes from setting things up intelligently. So if there's one thing to carry forward from this idea, it's this. Stop looking for the force that makes things move and start looking for the conditions that allow movement at all, because that's where real control in circuits and in life actually lives. By this point, another quiet misconception is ready to fall apart. The idea that electricity moves step by step, decision by decision, as if it were figuring out where to go. We imagine current leaving the battery, reaching a junction, then somehow choosing a path. We picture electricity reacting locally, piece by piece. But that mental movie is not how circuits actually work. Richard Feynman was very clear about this because it exposes a deeper flaw in how we think about cause and effect. A circuit does not operate sequentially. It operates as a whole. The moment a circuit is completed, the entire system responds, not eventually. Not one segment at a time. The electric field reorganizes itself across the entire circuit nearly simultaneously, limited only by the speed at which field changes propagate. Every charge responds to its local field, but that field is part of a global pattern that exists only because the whole loop exists. There is no point at which electricity is deciding where to go. This is especially obvious in circuits with multiple paths. People ask, how does the current know which branch to take? The answer is that it doesn't. There is no knowledge involved. The fields settle into a configuration determined by the geometry and resistance of the entire circuit. Current distributes itself accordingly, not by choice, but by consistency. This challenges a deeply ingrained habit of thought. We're used to linear explanations. First this happens, then that happens, then something responds. But electrical circuits don't wait their turn. They establish conditions everywhere at once, and behavior emerges from that structure. Feynman liked to point out that if you focus only on individual electrons, you miss the story completely. Each electron responds only to the local field. It has no awareness of the battery, the switch, or the bulb, yet the system behaves coherently, predictably, and intelligently, not because the parts are smart, but because the structure is. That's a powerful idea. It means order doesn't require control from the center. It doesn't require instruction. It emerges when constraints are set correctly. The circuit works not because something is directing it, but because the relationships between its parts leave no other consistent outcome. This also explains why partial thinking fails so often in electronics. You can't fully understand a resistor, a capacitor, or a wire in isolation. Their behavior depends on how they're embedded in the circuit. The meaning of each part comes from the whole. Psychologically, this is uncomfortable because it removes the comforting idea of local agency. We like to believe that actions have isolated effects, that problems can be solved one piece at a time, but electricity reminds us that many systems don't work that way. Change one connection and everything adjusts. That insight scales far beyond physics. Organizations, economies, ecosystems, even personal habits behave more like circuits than chains. You don't fix them by pushing harder at one point. You fix them by changing how things are connected. Feynman often warned against explanations that feel mechanical but hide systemic truth. Electricity is one of nature's cleanest demonstrations that behavior is not always driven. It's constrained. The circuit doesn't need instructions. It needs closure. Once the loop exists, the outcome is inevitable, and that reframes responsibility in an interesting way. If outcomes emerge from structure, then understanding structure becomes more important than blaming components. You stop asking which part failed and start asking whether the system made sense in the first place. So when you think about a circuit, don't imagine electricity traveling down a path like a messenger. Imagine the entire system snapping into a new state the moment it's complete. No delay, no decision, just consistency. And the reflection worth carrying forward is this: many of the problems we struggle with don't require more effort or smarter parts. They require better connections. Because when the structure is right, the system doesn't need to be forced. It works. If you step back and look at all of this together, it becomes clear that electricity is doing more than powering devices. It's quietly exposing a habit of thought that runs through almost everything we misunderstand about the world. We don't just get electricity wrong, we get reality wrong in the same way. We rely on metaphors because they're comforting. Water in pipes, forces pushing things around, decisions being made locally. These stories feel intuitive, so we stop questioning them. And that's exactly the danger. As Richard Feynman often pointed out, the problem isn't that these models are simple. It's that we forget they're models at all. We mistake them for the thing itself. Electricity punishes that mistake mercilessly. Every misconception we've talked about comes from the same source, treating a deeply relational phenomenon as if it were a substance or a sequence. We imagine in electricity as stuff instead of interaction. We imagine motion instead of coordination. We imagine force instead of conditions. And each time we do that, we end up confused, frustrated, or memorizing rules without understanding why they work. Feynman's real contribution here wasn't just explaining circuits more clearly. It was teaching a way of thinking, a way of staying suspicious of explanations that feel good but don't survive careful questioning. He insisted that if you truly understand something, you should be able to explain what it is, not just as clearly as what it is. Electricity teaches that lesson brutally well. Electrons don't rush. Energy doesn't live in wires. Voltage doesn't push. Circuits don't decide. And yet everything works beautifully, reliably, and precisely because the underlying relationships are right. That should make us pause. How many other areas of life are we misunderstanding because we're clinging to the wrong mental pictures? How often do we look for causes where there are only conditions? How often do we push harder when the real problem is structure? How often do we blame parts instead of examining the system? The deeper lesson here is intellectual humility. Nature does not care about what feels intuitive to us. It rewards clarity, precision, and the willingness to let go of familiar stories when they stop working. Electricity is one of the first places where that lesson becomes unavoidable, which is why it's such a powerful teacher. Once you really grasp this, learning stops being about collecting facts and starts being about refining perception. You stop asking, what is the thing doing? And start asking, what relationships make this behavior inevitable? That shift alone changes how you approach science, problems, and even personal growth. Understanding electricity properly trains your mind to think structurally rather than emotionally. It encourages patience over impulse, insight over force, and systems over shortcuts. That's why this topic matters far beyond physics classrooms and engineering textbooks. Electricity is reality politely warning you not to trust your first impression. So if there's one final reflection to leave you with, it's this: the greatest breakthroughs don't come from learning more facts. They come from abandoning the wrong stories. Question the metaphors you rely on. Examine the structures beneath them, and you won't just understand electricity better. You'll start seeing the world as it actually is.